Hello students, welcome to 6th lecture of structure of atom. So in previous lecture we discussed about drawbacks of Rutherford model and development of Bohr's atomic model, and in development of Bohr's atomic model we were actually discussing about wave nature of light radiation or electromagnetic radiation. So let us move further. So in our previous lecture our last point was Maxwell revealed that light radiation or electromagnetic radiation has this type of propagation in one direction, where electrical and magnetic fields are perpendicular with each other as well as with the direction of propagation of electromagnetic radiation. So although this electromagnetic wave motion is very complex, but here some few properties are mentioned for it. So let us discuss them step by step. So first is oscillating electrical and magnetic fields produced by oscillating charged particles are perpendicular to each other, and both are perpendicular to the direction of propagation of the wave, which we can see from the image mentioned. So simplified picture is mentioned. Unlike sound waves or waves produced in water, electromagnetic waves do not require medium and can move in vacuum. So as we know, sound waves do require medium for the propagation. In no medium it cannot travel. That means if you are creating vacuum, you cannot hear sounds, because molecules of air are responsible for the propagation of sound waves. So if vacuum is present, that means no air molecules are present, then no propagation of sound occurs, and that's why you cannot hear. So that it is a reason why we cannot hear anything in space. So next is it is now well established that there are many types of electromagnetic radiations which differs from one another in wavelength or frequency. So we already discussed about wavelengths. So this constitute what is called electromagnetic spectrum, which is mentioned in figure 2.7. Okay, so this is electromagnetic spectrum. All the way it starts from gamma rays to radio waves. Okay, so as we move from gamma rays to radio waves, wavelengths will start increasing like this. Okay, and as we can see, 10 raised to minus 16 meters to 10 raised to 8 meters. It is very large number. That means certain electromagnetic radiations may have 1 lakh kilometer equals wavelength. So it is very huge number. So radio waves have very high wavelengths. So in this case we have a very small portion of wavelengths or electromagnetic radiation, which is known as visible spectrum. Okay, it is mentioned here. So normally our visible spectrum will start from 400 nanometers to 750 nanometers. This is the range which we can see with our eyes. So this is called visible spectrum. This is the only portion which we can see. So as we can see, we have very large spectrum of electromagnetic radiation, and very small spectrum is actually we are able to see. Phone cameras can see infrared lights. As for example, suppose if we talk about our remote controls, so our regular normal remote controls uses light on top of it. So these lights actually produces infrared signals which can be detected by our TVs, and so that it can work. So when we place cameras on this type of remote controls, and when we press the button in remote control, we can see light producing infrared light, which we cannot see via naked eye, but we can see it using our phone cameras. So different region of the spectrum are identified by different names. As for example, radio waves around 10 raised to 6 hertz used for the broadcasting, microwaves around 10 raised to 10 hertz used for radars, infrared 10 raised to 13 hertz used for heating ultraviolet region around 10 raised to 16 hertz, a component of sun's radiation. Okay, we know that to prevent our screen damaging from the damaging of ultraviolet light, we should wear sunscreen when we are going in direct sunlight. Actually, sunscreens absorbs ultraviolet rays and it will prevent damaging our skin. So the small portion around 10 raised to 15 hertz is what is originally called visible light. It is only this part which our eyes can see or detect. Special instruments are required to detect non-visible radiations. So that means this small region known as visible spectrum, it is only a spectrum which we can see or detect. Otherwise, UV to gamma rays or infrared to long radio waves or radio waves, we are not able to detect this. We need instruments to detect. As for example, to detect radio waves or to identify or capture radio waves, we need radios, FM or AM as mentioned here. And different kind of units are used to represent electromagnetic radiation. These radiations are characterized by properties, namely frequency and wavelength. So SI unit of frequency V is hertz, Hz or centimeter inverse. After enrich hertz, it is defined as the number of waves that pass a given point in 1 second. Okay, so suppose this is our point, and at this given point we are passing some light radiation or electromagnetic radiation like this. So number of waves, that means this point to this point, we can consider this point as a single wave. So number of waves passing through this point in 1 second is known as hertz or Hz, or that's why it is unit of this is centimeter inverse. It is called hertz. So that means for radio frequency it is around 10 raised to 6 hertz. So we can say that 10 raised to 6 waves per second are passing through the point or given point. Similarly, as we going on right to left side, our frequencies will increase because wavelengths are decreasing. So microwave 10 raised to 10 waves per second, and in infrared 10 raised to 13, and for our visible light range it is 10 raised to 16 per second. And same thing in waves are mentioned here. So as we can see, 10 raised to 0, that means 1 per second for radio waves, to 10 raised to 24, that is it is extremely large number for gamma rays. Per 1 second 10 raised to 24 waves will pass at given point. That means gamma rays has extremely high frequency, and that's why energy of gamma rays is again extremely very high. So as the wavelength decreases, in energy of given wave or electromagnetic radiation increases. So energy and wavelengths, they are inversely proportional. So energy decreases, then wavelength increases, and wavelength decreases, then energy increases. So from this relation we can predict which of these wavelengths will be highest in energy and which of these wavelengths will be least in energy. So wavelengths, as mentioned, it should have a length and unit of length, and we know that SI unit of length is meter. So since electromagnetic radiation consists of different kind of waves of much smaller wavelengths, smaller units are used if required. So in figure 2.7, various type of electromagnetic radiations are mentioned which differs from one another in wavelength, and as we can see, we have large deviation in wavelengths. So in vacuum, all type of electromagnetic radiation regardless of wavelength travels at the same speed, which is 3 into 10 raised to 8 meter per second, and this figure seems familiar. or more precisely 2.997925 into 10 raised to 8 meters per second. So this is called light speed. Okay, our visible light is originally electromagnetic radiation. So speed of light is constant for each and every electromagnetic radiation. So when we apply different type of electromagnetic radiation in vacuum, then all of them will travel at the equal speed, doesn't matter what is its wavelength. So symbol of the speed of light or constant is c. The frequency, wavelength and velocity of lights are related by the equation 2.5. So c is equal to v lambda, that means frequency into wavelength is equal to speed of light, and this is constant for each and every lights or electromagnetic radiation. And other commonly used quantity is especially in spectroscopy. Now spectroscopy is a branch of chemistry which studies with light or electromagnetic radiation. Okay, or spectra, that means a series of different type of wavelengths. Is the wave number v bar. It is defined as the number of wavelengths per unit length. Its unit are reciprocal or wavelength unit, that is meter inverse. However, commonly used unit is centimeter inverse, not SI unit, because wavelengths are very small. So one problem is mentioned. The Vivid Bharati station of All India Radio Delhi broadcasts on a frequency of 1368 kilohertz. Kilohertz, that means 1 kilohertz is equal to 1000 hertz. Kilo word actually represents 1000 in Greek. Okay, so whenever we use kilo prefix, it represents 1000. So calculate the wavelength of the electromagnetic radiation emitted by the transmitter. Which part of the electromagnetic spectrum does it belongs to? Okay, so we have only frequency of this electromagnetic radiation, which is 1368 kilohertz, and our target is to find wavelength and in which part it belongs. So as mentioned earlier, relationship between speed of light or constant c is equal to wavelength into frequency, that means frequency v into wavelength lambda. Now we know that c is a constant value and value of v is already mentioned, so we need to find lambda in this case. So our equation will be lambda is equal to c upon v. Now we already know that the value of c and value of v is mentioned here. So c is equal to 3 into 10 raised to 8 meters per second, and divide by v is equal to 1368 kilohertz. Now as mentioned earlier, we can use hertz or centimeter inverse. So that means we have to convert this kilohertz into hertz, because our first value or c uses second as unit. Okay, so we have to use second unit, that means common unit for both of the value. So that's why our value will be 3 into 10 raised to 8 meter per second divided by 1368 into 3 second inverse, that means second inverse or hertz. Okay, that means we converted kilohertz into hertz, and that's why we multiplied it with 10 raised to 3, and it is equal to 219.3 meters. Okay, so this will be wavelength of given electromagnetic radiation, and 219 is equal to 2.19 into 10 raised to 2 meters. So this wavelength belongs to radio waves, or specifically nearly in AM range. Okay, next one is a wavelength range of a visible spectrum extend from violet 400 nanometer to red 750 nanometer. Express these wavelengths in frequencies or hertz. 1 nanometer is equal to 10 raised to minus 9 meters. So in this case wavelengths are mentioned, and our equation or relationship between wavelengths and frequency is C is equal to lambda into V. Okay, so in this case wavelengths are mentioned and we need to find frequencies. So our equation will be V is equal to C upon lambda. Okay, so all you have to do is place the value of C, which is already known, and divide it with the lambda, which is provided in the question, and you will get your answer. Okay, so this is a easy question, so we are not going to discuss it step by step, but if you find any confusion you can ask me. So let us move on. Last one, calculate first wave number and second frequency of yellow radiation having wavelength 5800 angstrom. So first we have to convert it into common value, or which can be used by us. So angstrom is equal to 1 angstrom is equal to 10 raised to minus 8 centimeters or 10 raised to minus 10 meters. Okay, so this will be the values in centimeter and meter. So as we know, frequency wave number is equal to inverse of wavelength. So V bar is equal to 1 upon lambda, so it is equal to 1.724 into 10 raised to 6 per meter. Now our second part is frequency. So our equation will be V is equal to C upon lambda. Here V bar is mentioned, but actually it will be V is equal to C upon lambda. So divide speed of light with lambda, which we have already done in previous numerical, and you will get your frequency. Now our next point is particle nature of electromagnetic radiation, Planck's quantum theory. So we already discussed about wave nature of electromagnetic radiation, and now we are moving on particle nature, because waves contains both electromagnetic radiation contains both type of nature. That means wave nature as well as particle nature. So some of the experimental phenomena such as diffraction and interference can be explained by the wave nature of the electromagnetic radiation. Now what is diffraction and what is interference? So let us discuss it first. So at the bottom of the this page, some basic information is mentioned. Diffraction is the bending of wave around the obstacle. And second thing, interference is the combination of two waves or of the same or different frequencies to give a wave whose distribution at each point in space is algebraic or vector sum of disturbances at that point resulting from each interfering waves. Now what it represents, let us discuss it with some illustrations. So this is the example of bending of wave. As mentioned, diffraction is a bending of wave around the corner. So as we can see, we have a straight wave in two different scenario. So let us discuss first. So as we can see, we have comparatively wide slit or opening. So our initial waves are coming straight, but when they come in contact with this slit, they start bending and spreading. That means if we stretch a straight line, you can see waves are getting bigger and bigger. Intensity of these waves will decrease obviously because they are spreading out, so energy obviously decreases, but sizes of this wave passing through this slit will increase. And bending of wave even depends on size of slit. If size of slit is even smaller, it will bend even more. So as we can see in second case, we have comparatively smaller slit and we have straight waves. When these straight waves come in contact with this smaller slit, it will bend even more. Okay, so bending of wave will be comparatively increased, and you can see this type of result. Okay, so this is called diffraction, and diffraction is the reason why we can see different colors when light passes through the prism. When white light or sunlight passes through the prism, different type of colors are obtained, as we can see in this image. Okay, so we have a white light source which is producing just a white light, and diffraction grating, that means it is a one type of glass instrument which can separate out the wavelengths of light. So this white light, when passing through the slit, as mentioned in previous image, this is our light, and this is our slit, that means small opening. So when these parallel light waves come in through went through this small slit, it will start bending, that means it will spread out. Okay, so this is the result when white light spread out. Different type of colors will be separated out from each other. So this is the diffraction of light or electromagnetic radiation. And this is the actual photograph of practical we discussed. Okay, so this is the white light diffracting, that means it is when it is passing through the small opening, it will spread out or it will bend. That's why we can see this type of different colors. And this is the diffraction of light from prism. From the one side white light is coming, that means this is the direction of white light coming, and then it will spread out in different colors, that means diffraction. And this is the example of interference, that means two different waves interacting with each other. So we have two different possibilities for the interaction. As we can see here, we have two, in first case we have two same type of waves and they are aligned with each other exactly the same. So that means if one is going upward, then second is also going upward, and when second is going downwards, first is also going downwards. So that means both of these waves will support each other. That means according to algebraic summation, suppose energy of first wave, that means let us call this wave A and second wave B. So energy of first wave A is, let us say, 1, and energy of second wave B is, let us say, same, so that's why it will be 1 as well, and both of them are supporting each other, so we have to add them into each other. So this is going to be 2. So resulting wave will have comparatively higher energy, like this. That means it will be more intense than the previous waves. Okay, so that means A and B both are adding up into each other, and you will get a stronger wave. So we can see it here. In the second case, we have again same type of wave. First wave, let us call it A, second wave, let us call it B. Again, both of them are equal in energy, so energy of A is 1 and energy of B is also 1. But difference is they are opposing each other. If first wave is going upward, then second wave is going downwards. If first is going downwards, then second is going upwards. So they are opposing each other. Okay, so eventually we have to subtract it, as mentioned, algebraic summation or subtraction. So here, if first wave is +1, then second is opposite to it, that means it must be -1. So summation of both of them will lead us 0. So as a result, you won't get any outcome. Okay, no waves will be obtained if both of them are opposite to each other and both of them have same energy. So this is one good example of noise cancellation. When we have two exactly same type of speakers having same type of strength, and both of them are emitting exactly the same type of waves, but like this, opposite waves. So as a result, no matter what is the level of the volume of speaker, it is very high or low or medium, we will be unable to hear sound coming through them, because both of them are actually cancelling out each other's effect, and you will only here is a silence. Now two different waves, when these two different waves are supporting each other, resulting wave will be comparatively more in energy than the previous. This is called constructive interference. Okay, when two different waves are supporting each other and resulting wave will be more in energy, and when two different waves are actually opposing each other, this is called destructive interference. In destructive interference, a resulting wave will be lower in energy. Okay, in constructing they are supporting, that's why resulting will be more in energy, and in destructing interference they are opposing each other and resulting wave will be less in energy. Now practically speaking, this is the example of constructive and destructive interference. So as a starting point we have, let us say, almost parallel sunlight, and when this sunlight passes through this slit or small openings, as mentioned earlier, because of diffraction they will bend. Okay, so this is the example of diffraction here, from here. Okay, from this opening it will start diffracting. Okay, so we have two openings, so two different waves will start diffracting, and that's why two different waves will be produced from these two opening. Okay, and they will spread out as mentioned earlier in case of diffraction. So eventually both of them will meet like this. Here we have common region where both of these waves are interacting. So at some points they will constructively interfere, and some point they will destructively interfere. So when they both of them are same type of wave, so when they are meeting with each other constructively, you will see comparatively bright spot, and when they meet with each other destructively, you will see no light. Okay, so because of this type of interaction with two adjacent slits and the same type of light when passing through these slits, you will see these type of patterns. Okay, actually you will see these type of patterns. So that means, how can we create this type of practicals? Put a box in a sunlight, poke two different holes close to each other, nearly 3 to 5 centimeters apart, and when we try to see light coming through these two different holes inside the box, you will see these type of patterns. That means bright spot, dark spot, bright spot, dark spot. These type of pattern will be observed inside the box. So practically you can see these type of result from these two split experiment or double slit experiment. Okay, so as we can see, we are providing continuous light, and the end result will be like this. That means dotted line. When constructive interference occurs, we will see these type of bright spots, and where destructive interference occurs, you will see these type of dark spots. Okay, so this is double slit experiment. Okay, so these type of results can be expressed from the wave nature of electromagnetic radiation. However, following are some observations which could not be explained with the help of even electromagnetic theory of 19th century physics, known as classical physics. So some points are mentioned. We will discuss these points only in this lecture, and later points we will discuss in next lecture. So first, nature of emission of radiation from the hot bodies, black body radiation. So what is black body radiation? We will discuss it. Ejection of the electrons from the metal surface when radiation strikes on it, photoelectric effect. Simple example, solar cells. Solar cells ejects electrons using sunlight. Next, variation of heat capacity of solid as a function of temperature. And the last one, line spectra of atoms with special reference to hydrogen. So what these all points represents? We have 4 different points which cannot be explained using wave nature of light or electromagnetic radiation. Okay, so we will discuss all of these practicals step by step in detail in next lecture. Okay, if you have any confusion till this point, you are free to ask.